Now we're going to look at how we apply Newton's second law to figure out the forces involved in making something go around in a circle. So here's going to be a typical problem where we have something sitting on the surface and something is going around. So we have here something sitting on the surface out here and it's going around this circle. So first what we need to do is look at the two directions. The y direction in this case is just our normal force and our weight because we're standing on a horizontal surface. And then we need to change our variable from x basically to c, as this is our center seeking force, and we are in fact accelerating as we're going around. This will probably make a lot more sense with a couple examples, and that's exactly what we're going to do. So here we have an example problem where we have a coin on a record. That coin is sitting somewhere on the record, and we want to figure out at what distance r we can place that coin so it doesn't fall off as it goes around. We know that the velocity is 33.3 RPM, so that's omega, but we're going to need to at some point convert that to radians per second, and we know the coefficient of friction. 0.1 is not very much, it's going to be pretty slippery, so it's not going to take all that much force to get this thing to fall off. First thing we need to do is start with a free body diagram. I'm going to model my coin as a dot. It is on the planet Earth, so there is weight down and a normal force up. And then to get it to go around, there needs to be some sort of force to get it to go around in the circle. That happens to be the force of static friction because it is not slipping. If there is no force, as we saw, it will go in a straight line. So there's got to be some force to get it to go around the circle, and that has to be friction because there's nothing else holding it on. So then we do force balances, sum of forces in the x direction, or we call it sum of forces in the centrifugal direction, is equal to MAC. And we need to pick a form for our AC. Remember that AC is equal to omega squared R or V squared over R. So in this case, we're given something that looks very much like omega. So we're going to choose the form of the equation with omega. And we know that that force that's operating in that direction is my force of static friction is equal to m omega squared R, where again, this is AC. And then if I sum my forces in the y direction, I have my normal force minus my weight is equal to 0 because there's no acceleration in that direction. It's just sitting there going around at the same height. So that means my normal force is equal to my weight is equal to mg. Then I can go back up and look at my horizontal formula. We also know that Fs is equal to mu n. So if I take that and stick it down here to have a little bit more room, mu n then is equal to m omega squared R over, should I put that there? M omega squared R, and n we know is equal to mg. So we get mu times mg is equal to m omega squared R. Nice, we can cancel masses out, so it doesn't matter if it's a penny, if it's a dime, we don't care what the mass is. And then we can solve for eventually R, because that's what we want to find is how far from the center. That looks like an R, or an R. It doesn't matter if it's upper or lower case. R then is equal to mu of static friction times g over omega squared. Now I have most of these values. This is 0.1 times 9.8 meters per second squared. And then we get to the point of plugging in omega and find that we really need this to be in radians per second before we square it. So we're not given that in radians per second, so we need to go back and fix that issue. So we take 33.3 revolutions per minute. And again, we need to divide by revolutions, multiplied by radians. There's 2 pi radians per 1 revolution. And we have We need to cancel out minutes, so we put minutes up here and seconds down here. There's 60 seconds per minute, and that gives us 3.5 radians per second. So I put that there and square it, and I get 0.081 meters, or 8.1 centimeters. So here, the distance I can place it is 8.1 centimeters. Now, if I look at this formula, if I make, I go back up here, mu g is equal to omega squared r. If I make r bigger, then it's going to have more tendency to slip off. So the force is going to be bigger. And if I make omega bigger, if I spin it faster, then basically if I make omega bigger, I have to make r smaller for the penny to stay on. And here are all those values a little nicer written out. And then now we're going to work on this problem. Is we have somebody swirling a slingshot around in a horizontal circle, so we don't have to worry about the vertical direction. And we know the radius. This is r, because that's how long the string is, and it's moving at 180 RPM, so that should give you indication that that is omega, and we're going to need to convert to radians per second at some point. So in this problem, what we have going on is, first thing to start, as with any other problem, is a free body diagram. So here we have the slingshot, and we have tension going in this direction. Now things get a little bit complicated in the y direction. That the reason why it stays up is because of momentum. So yeah, there is weight here, but we're not going to get into that. We're going to look strictly at the force balance in the x direction. So sum of forces in the x direction is equal to MAC. And again, AC is either equal to omega squared r or mv squared over r. And we're going to use the omega squared version because I have an omega here. And the force providing the centrifugal force is tension. So tension is equal to m omega squared r. And again, we're going to need omega. So I'm going to take that 180. Omega is equal to 180 revolutions per minute. And multiply out the 1 revolution for 2 pi radians. And the minutes over seconds gives me 60 seconds, and that gives me a speed of 18.24 radians per second. And then I can solve for my tension. Tension is equal to that mass of 0.1 kilograms times my omega is 18.24 radians per second squared. And my radius is the 2 feet, or 0.6 meters. And that gives me a value of 19.96 newtons, or about 20 newtons of force in order to keep that string twirling. And again, if we look at these variables, and changing any of these things will increase the amount of tension required. If the mass goes up, more tension. If the speed I'm spinning it goes up, there's more tension. If the circle gets bigger, there's more tension. So you can give this a try at home, take something and twirl it, and see if you can twirl it faster, and find that it takes more tension. You'll feel more tension on that wire as you spin it faster. Here's all those numbers all nice and written out, and on to the next section.